when it comes to reactions, haloalkanes are very different from hydrocarbons because, unlike hydrocarbons, they are polar. So if we take a simple example like chloromethane, that bond is polar because chlorine is much more electronegative than carbon. So you get this. And that makes all the difference because that delta positive carbon is a weak point. That's something that other things can home in on and attack. And we'll see how that works in detail when we look at the mechanism in a bit. But for the moment, we'll just look at really the one reaction that we're going to learn for the moment, although next year you'll learn several more which you'll see are closely related to this one. But the reaction you need to learn is with sodium hydroxide. So if we take our chloromethane and we add aqueous sodium hydroxide, we get a substitution reaction in which basically a Cl- ion leaves and an OH- ion replaces it, and so we get a substitution in which the halo group is replaced by an OH group, and we get sodium chloride as the other product. So that's a substitution, but it's very different from the radical substitution which you've learnt for alkanes reacting, and we'll see that in detail when we look at the mechanism in a bit. But for the moment you just need to learn that that's the case. No special conditions for that, you just need aqueous sodium hydroxide and it goes relatively smoothly to make the alcohol and sodium chloride. You can also do the same thing with water and you get a very closely related reaction which goes like this. So you have H2O and you get the same product because the OH from the water, or OH minus if you like from the water, substitutes for Cl minus there. So again you get CH3OH, but this time instead of NaCl you get HCl. So these two reactions are closely similar. This one is slower, and we'll see why when we look at the mechanism, but they both achieve the same thing, and they're both examples of a reaction called hydrolysis. This is a kind of very vague word really, which is used a lot in chemistry to mean any reaction in which a substance is broken down by reaction with water. Now you can see in this one, you know, in some ways it's not reacting with water, it's reacting with sodium hydroxide, but it does have to be aqueous, and it's the fact that the water is there that makes the reaction favourable. So it's categorised as the same thing. So hydrolysis is a slightly vague term, but it means a reaction in which something is broken down by reaction with water, but that often will include reaction with an aqueous alkali like that. Okay, so those are the reactions that you need to know. Now when it comes to the mechanism of those substitution reactions, as I say, the key to it is the polarity of the molecule. So if we start with this compound and put the dipole on there, and then if here is our hydroxide ion, you can see that there's going to be attraction between the negative charge on the hydroxide ion and the delta positive carbon there. And in particular, the hydroxide ion has lone pairs. It actually has three, but it only needs one to mount the attack. And that lone pair is going to home in on that carbon and ultimately make a bond to it. So you get a curly arrow that goes like that. Remember, a curly arrow means movement of a pair of electrons, so it's that lone pair is the pair of electrons and it's mounting an attack on that carbon to make a bond to it. And because carbon can't form 5 bonds, if it's going to accept this incoming pair, it's going to have to boot out another pair, and the one that's going to go is this one, because that will result in the formation of Cl-, which is a relatively stable, favourable ion. If it broke one of the other bonds, you'd get H-, which is a much more improbable thing to get. So this is what happens. So you get the pair of curly arrows, which is quite reminiscent, remember, of electrophilic addition, where you get one pair of electrons moving in and nudging out another pair. It's a very common thing in organic mechanisms. So one pair comes in to form a new bond to the carbon, nudges out this pair. And so the upshot of that is that you'll now have your CH3OH molecule with that new bond in place there, and the chloride will have left as Cl-, because instead of just having a half share of this bonded pair, it's now got that pair entirely to itself, so it's become Cl-, and we show that new lone pair like that. And that's it. So this is a very particularly simple mechanism because it's all over in one step like that, no intermediates at all. So learn that, make sure you get the details right. You need to have the dipole shown, you need to show the lone pair being used to mount the attack, and also the new one being formed. And critically, you've got to get the curly arrows exactly right. So going from the lone pair to show that it's moving to the carbon, and this one coming from the bond to show that it's breaking and becoming a lone pair. So the OH- in this mechanism, you can see, is acting as an electron pair donor, because it's donating a pair of electrons to attack the carbon. And you'll see how that contrasts with the electron pair acceptor that we had when bromine, for example, attacked an alkene, where it accepted an incoming pair of electrons. So this is not an electrophile, but rather something else, an electron pair donor, and the word we use for that is nucleophile. Okay, so that's another new word that you need to know. A nucleophile is an electron pair donor, and that's what the OH- is doing. So this mechanism is called nucleophilic substitution. Okay, and you need to learn that. Term. The reaction with water has essentially the same mechanism, but once the water attacks, it has to lose an H+ ion. They're unlikely to ask you the mechanism for that, so just focus on learning this one. One very interesting question that we can ask in relation to haloalkanes is, how much difference does it make which particular halogen we have? So if we compare, for example, one bromopropane with one chloropropane, they will both react in the same way with water or with OH- to form the alcohol plus, releasing Br- or Cl-. But the question is, do they do so equally readily? So it would be good to devise an experiment that lets us compare the rate of the reaction. So we could compare OH- reacting with each of these to give you the same product in both cases, but releasing Br- in this case, or Cl- in this case. So if you're going to do that, what you need is a method to detect when either the alcohol is formed or the halide ion is formed, because then you can monitor the rate of reaction by detecting how quickly one or other of these products is formed. This is not particularly easy to detect because it's not coloured or anything, but you already know how to detect these because you've learnt the test for them, which is that if you add silver ions in the form, for example, of aqueous silver nitrate, they precipitate out to give a cream precipitate of silver bromide in that case, or a white precipitate of silver chloride in that case. And that gives you a method to follow the rate of reaction, because so long as the halogen is bonded in a covalent bond to a carbon here, it can't react with silver ions. So until this is reacted, these halogens are protected from the silver ions by that bond. But as soon as they're released, the precipitation occurs essentially instantly. So you can follow the rate at which the precipitate forms as a way of monitoring the rate of this reaction. Now the only snag is that you can't use hydroxide ions in the presence of silver because it precipitates out silver oxide, which is going to interfere with the reaction. So you do the reaction with water instead. So you do this reaction for both of them, which means that you produce HBr or HCl as the other product. But it works the same way, because of course HBr in aqueous solution is ionic, so you could write it like this, as H plus aqueous plus Br minus aqueous, and the same here as H plus aqueous plus Cl minus aqueous. And so these, as soon as they're formed, precipitate with Ag plus aqueous. So it's kind of a clever experiment, because it uses this trick you've learnt before just as a test for the halide ions, but now it's using it as a method for detecting how quickly these ions are formed in the reaction. So, as I say, this is an unusual case where you actually have to be able to describe the experiment for doing this. So what you do is that you prepare a solution containing, and you need basically three components. You need the haloalkane, you need aqueous silver nitrate, and the least obvious one is that you also need ethanol. Now the reason for the ethanol is that, as we discussed earlier, haloalkanes don't dissolve in water. So if you just made this mixture, you'd have two layers, the haloalkane and the aqueous silver nitrate. And then the rate of reaction would depend on how good you were at mixing, basically. How good you were at making the two layers mix together. But the clever thing is that both the haloalkane and the aqueous silver nitrate are soluble in ethanol. So the ethanol is there as a solvent, because rather helpfully all of these things will dissolve in it. So by preparing that mixture, you just get a single phase, and that means you don't have to worry about the mixing side of things. So you prepare a solution containing that, and then you incubate in a water bath or any kind of thermostated environment. Incubate just means you stick it in something at a controlled temperature for however long it takes. In this case, monitor how long it takes for the precipitate to appear. And the idea is that you compare chloro, bromo and iodoalkanes. Okay, so that's the experiment, and now we want to look at what the outcome is. So if you compare the rate of hydrolysis of these three haloalkanes using that method that we've just talked about, what you find is that this one reacts slowest. In other words, the white precipitate of AgCl takes longest to form. And as you go down the group, it gets faster, so this reacts fastest. So the yellow precipitate of AgI forms much quicker. Okay, so that's an interesting result which you need to know, that the iodoalkane is the most reactive and the chloroalkane is the least reactive, but you also need to know why. And that has to do with the strength of the carbon to halogen bond. Because in the reaction, obviously that bond has to break, and the stronger it is, the harder that is to achieve. Later on, when we look at reactions you'll learn about the idea of activation energy, which is the energy that has to be put in to break some existing bonds before new ones can be formed. And this is a very good example of reactions which differ in activation energy as a result of the strength of the bond being broken. So what we can say is that the reactivity increases from the chloroalkane to the iodoalkane because the bond strength decreases. So in other words, if we put those carbon to halogen bonds in order, the C-Cl bond is the strongest and therefore the hardest to break, and then CBr, and then Ci is the weakest. Okay, so you need to remember the experiment for investigating this. You need to remember the outcome, that this is the least reactive, this is the most reactive, and you need to learn the explanation in terms of the strength of the bonds that need to be broken.